Okay, so we're going to kick things off now. We're going to start talking about reverse engineering. So this is going to be the first part in kind of a 3-week series where we're going to be diving into kind of how programs work at a low level and how we can use or abuse that knowledge to make those programs do things that they don't want to do. So reverse engineering, or as it's often abbreviated, RE, is basically just figuring out how a program works. And so that's really useful in situations where you want to either use that knowledge of how it works to exploit it, to find bugs, which you can then leverage, or even in cases where you're looking at malware and you want to figure out exactly how that malware works, so that you can figure out how to stop it and how to prevent it. So reverse engineering is an incredibly broad skill set that's useful in a lot of different contexts. The one that we're going to be focusing on for the most part is binary exploitation, or as it's often abbreviated in CTFs, pwn. And basically the idea of that is, as I was alluding to before, you get to know this program so well. You get to understand how it works at a really deep and fundamental level, and then you can use that knowledge to take control of that program. And so you can use that to exploit vulnerabilities, to find vulnerabilities, to take control of it. And so that kind of begs the question of how that works. And that's something that I want to add a quick disclaimer to. I want to point out that this is a kind of complex topic. It's a little bit more complicated. The barrier to entry is a little bit higher than a lot of the other things that we've talked about so far in the semester. And so if at some point, if you're lost or anything like that, or if you have questions, we have a live chat. You're welcome to pop questions in there. We'll have someone answer them. And you're also welcome to join our Slack and ask questions there. So with that out of the way, you do kind of need a bit of a foundation. You do need a bit of background knowledge to understand how things work. And so a lot of those concepts are things that you can get from the classes at RPI. So for example, if you've taken computer organization or CompOrg, or even like Coco or Knos, which are the more hardware-oriented alternatives to that, a lot of the things that we'll be talking about today are going to look really familiar. And if you haven't, and you have taken something like data structures, there are times where we will be talking about like how pointers work, or how functions work, or how the stack works. And those are things that will probably make a lot more sense if you kind of have that background, if you've kind of looked at things from that perspective before with the lower level programming. That being said, we do our best to teach these concepts as well, so you don't have to have taken comp or data structures even to understand what's going on. And that's really the main point of a thing like this that we're doing today, of IntroSec, where we want to lower the barrier to entry. We want to explain this as simply as we possibly can. So with that being said, I want to devote a little bit of time to just talking about how computers work. And again, if you've taken CompOrg, a lot of this is going to be pretty familiar. Basically, when you run a program, that's consisting of a lot of different instructions, and those instructions are executed on your CPU. So those instructions can be telling the CPU to do things like comparing numbers, or doing arithmetic, or calling another function, or things like that. But kind of alongside those instructions, you have data. And so that data is going to be a little bit more dynamic. That's going to be the things that those instructions are being operated on. So for example, if you're doing arithmetic, you need some form of data to know like a plus b equals 5. So you need to know like what a and b are. And so as a rule of thumb, instructions are pretty much going to stay static. Those are going to stay constant. Like when you start your code, the instructions are going to be the same as when you finish your code. However, the data is going to be changing all throughout that program. However, both these instructions and the data are both stored in memory. So if you have a computer and you have, say, 8 gigabytes of memory or 16 gigabytes of memory, that's basically storing all of this data, all of this code. So whether that code is your operating system or that code is whatever program you wrote for homework, that's all just getting yeeted into your computer's memory. In addition to that, it has a CPU, and that's what actually does all of the hard work of executing those instructions. So when you're saying, like, add A plus B, that arithmetic, that addition, is happening on your CPU. However, it does also have some form of storage on board. So we've talked about how memory is a form of storage, and you can store entire programs in memory. But the CPU has things called registers, which are like little tiny buckets that can store much smaller amounts of information. However, the advantage to these registers is that they are incredibly fast, because that code is also being executed on your CPU. So when it needs to access a register, it doesn't need to go very far, but when it needs to access memory, that's a much further, that's a much bigger delay, because that information needs to travel a lot further. Another thing we want to talk about is kind of what these programs can look like and how they're structured. So you've probably heard of 32 versus 64-bit programs and 32 versus 64-bit architectures. Fundamentally, they're more or less the same. There are a couple of subtle differences, but for the purposes of this talk, we'll be talking about 32-bit because it's a little bit simpler. Basically, what 32 versus 64-bit means is how big your pointers are. So if you've taken data structures, you know that a pointer is just something that points to a space in memory. So if you have a bigger pointer, you can have more memory. So in the case of a 32-bit pointer, that pointer is going to be 4 bytes long, or 32 bits, because 32 divided by 8 is going to give us 4. In the case of a 64-bit system, we're going to have 64-bit long pointers, or 8 bytes long. Each of those bytes can be represented in hexadecimal, and because hexadecimal is base 16, that's going to give us 2 different digits there for a single byte. So for example, if we want to say, like, we can represent a byte as like 0x41 or something like that. And because we know that on these 32-bit programs that we're going to be looking at today, the addresses are going to be 4 bytes long, that means that we can represent a pointer with 8 characters. So we can see that down here. That's going to be what a pointer is going to look like for us. Now ranges of those memory addresses are going to specify a different section of memory. So for example, where your code lives in memory is one section of memory. Where your stack lives is another section of memory. We're going to be talking about both of those sections in more detail in a little bit. So now that we've kind of talked about the structure of the program and how these things work a little bit at a very low level, I want to talk about how these things get executed. So if you've taken Comporg, if you've taken computer organization, you might remember this 5-stage CPU pipeline. And that basically says that you're going to fetch that instruction, you're going to decode that instruction, you're going to execute it, and eventually at the end you're going to write that information back to memory. Basically, every single time you run an instruction, you're going to be doing these steps. You need to fetch that instruction from memory, you need to read it, you need to do something, and then depending on the instruction, you might need to move some memory or some value back to memory, and then you move on to the next instruction. You just do that in a big loop that happens over and over again. So now that we've talked about all of that stuff, I want to tell you about how you can actually read this assembly. You can read these instructions. Basically, when you have a piece of code, when you compile it, one of the steps there is it's going to be compiled into assembly. And assembly is basically what the CPU actually executes. It's very closely mapped to that actual just stream of bytes that goes into your CPU. However, it's a little bit easier for us to read. And so oftentimes when we're trying to reverse engineer something, the highest level that we can actually get that to, the most human readable level that we can actually get that code to, is assembly, because it's mapped so closely to what your CPU actually is able to understand. And so because of that, it's really, really important for us as reverse engineers to know how to read assembly. And so I want to talk a little bit about different disassemblers. So there's IDA, which we can see the logo here on the right. This is kind of a meme in the security community about how IDA is this incredibly expensive piece of software, but now it has actual competition. So Ghidra is what I would actually recommend a lot of people start out with, because it's completely free. It's totally open source, and it's a really powerful piece of software that lets you take apart other programs and figure out how they work. Another really amazing player in the game is Binary Ninja, which is not completely free. However, it's much more affordable, and there are a lot of cases where if you're trying to do more complex analysis, it actually makes a lot of sense to be using Binary Ninja. So these are kind of the big players for when people think about like disassemblers and tools to be like helping statically like look at this code. However, if you think about it, GDB is actually also a disassembler. If you've ever like compiled your data structures homework without that -G flag, and you set a breakpoint and you see all this like RAX equals whatever nonsense, that's because GDB is actually disassembling the program that your CPU is trying to execute, and it's lifting it into assembly because that's the highest level that it can lift to, and so it makes debugging easier than if you're just looking at a stream of bytes. So the next thing I want to talk about is kind of the format of these instructions, now that we know what an instruction is and how it's formatted, or and things like that. So we're going to be focusing on the type of syntax that most people use, which is was pioneered by Intel. There are other types of there's other ways that you can format these instructions. And so I think GDB out of the box might try to do it a little bit differently, but if you're using the tools VM, we should already have it set up to print these instructions out in Intel format. And if you're using any of those other disassemblers that we were talking about just a second ago, those should be printing them out in Intel by default. So in Intel's syntax, you have that instruction. So that might be something like a move, or it might be something like an add. And then you have the destination register followed by the source register. So for example, if you have a move instruction, if you're trying to move something from EAX, or from something that's pointed to by EAX in this case, into EDX, that's what it would look like. You would have move, destination, source. However, there are a lot of different types of instructions. So on this slide, we have a really common map, a really popular map of all of the different types of instructions. So on the vertical axis, we have that first half of the byte, and on the horizontal axis, we have that second half of the byte. So for example, if we go down here, we can see 9, 0 is going to be a NA. It's also worth noting that if you look over here, in this corner, you can see that there are instructions that actually have multiple bytes. So there are instructions of varying length, and that's kind of an interesting quirk of x86. If you've taken computer organization or something like that, you may remember that all instructions in MIPS are the same length. Well, unfortunately, we don't have that same convenience for x86. Things can get a little bit more complicated. So yeah, there are a lot of different types of instructions. You don't really need to know all of those. We're going to be talking about kind of the most common types of instructions that you'll probably see today. And realistically, this is probably 90 to 95% of the instructions that you'll see on a daily basis. So the most basic ones, which we kind of alluded to before, are arithmetic instructions. So the first one is a move, and I'd kind of be a little bit hesitant to say that's even an arithmetic instruction. Basically, it's just moving one value, one value into a register. So for example, here we are moving 0, we're moving the value 0 into the register EAX. Another really common one is like subtraction or addition or multiplication, things like that, more common like traditional arithmetic. So right here we're saying subtract 1 from the register EAX. Subtract destination source. So we can kind of put that to the test a little bit here. If this was a normal semester where we were allowed to gather in person, if we were all sitting in the same room looking at this on a projector, this is the point where we'd kind of freeze and we'd say, like, we'd work through this together and we'd all figure out as a group what this section of code was doing. Unfortunately, we don't really have the ability to do that so much because this is remote and this is just being live streamed. So if we're pretending that every instruction is 1 byte in size, at address 0 we have this move, and then at 1 we have this second move, so we're setting EAX, EBX, and then we're adding the 2. So we're storing 2 in EAX, we're storing, because EAX is in the destination, and 2 is in the source, we're storing 2 in EAX, we're storing 1 in EBX, and we add EAX and EBX. Another really common type of instruction is a jump. So that's basically just going to tell your CPU to jump, to divert execution to wherever that register is pointing, or wherever that destination is. So for example, jump EAX will jump to whatever EAX points to. Oftentimes you'll see a hard-coded value in that destination field. So for example, if we look at this code, and this is kind of where those addresses become a little bit more important, we can see here we move 0 into the EAX register, and then this next instruction is we jump to 3. So right here, this 2, normally we would move 1 into EAX, but because we're jumping, we're just going to skip over that OX2. We're going to skip over that address completely, and we're going to go straight to the next instruction. We're just going to be moving EAX into EBX. So at the end of this section, after all of this code gets executed, we're going to move 0 into EAX, then we're going to jump to the line here, where we're going to move EAX into EBX. So at the end of all of this, we're going to have that value 0 in EBX. So another thing that you see really commonly in conjunction with those jumps is a compare, or some kind of way to have that control flow, that kind of conditional, if you will. And that's kind of the assembly equivalent of an if statement. So one really common thing that you see is a JNZ, or a jump not 0. And you see that a lot of the time with a compare instruction. So this is going to say, are EAX and EBX the same in this case, because we have EAX and EBX as the 2 arguments to that compare instruction. And if they are equal, it's going to set a special register, essentially. It's going to set a special flag, which is basically just another special register. And then the JNZ, the jump not 0, will check that flag, and if that flag is not set, then it will jump to whatever that destination is. So that part is going to look really similar to the code that we looked at before. So this is a little bit more complicated than the last example. We're going to be moving 0 into EAX, and we're going to add 1. So we're going to increment EAX by 1. We're going to compare it to 10, and then we're going to see if 1 is in EAX, and 10 is what we're comparing it to. They are not equal, so that 0 flag will not be set, which means that jump not 0 will take place, and we'll jump back to address 1 here, and we'll keep going through here over and over and over again until we finally increment EAX up to 10. So if you think about it, this is kind of what a for loop looks like in assembly. You can start to see how some of these more high-level constructs that you might remember from like Python or C++ or Java or whatever you prefer languages, you can kind of see how those map into assembly, how you can kind of do the same exact things at a much lower level. So yeah, as we were talking about before, that's basically just going to be setting these values, incrementing them, comparing, and then doing that conditional jump, that jump if and only if EAX is not equal to 10. So now we've kind of talked about control flow, and we've talked about basic arithmetic instructions. So the next thing that I really want to talk about is memory, which is kind of how you store and read bigger pieces of data. So we were talking before about how registers are really great because they're really fast, but they're kind of small. You can't store a lot of information in them. So like we're talking about, these are 32-bit registers. This is a 32-bit program we're looking at. So you can only store 32 ones or zeros, or 4 bytes in each register. Oftentimes, you're going to be dealing with much bigger pieces of data. And so you kind of have to put that data somewhere in your computer's memory. And the way that you do that, or one of the ways that you do that, the way that we're going to be focusing on right now, is through pushing and popping values. So if you're familiar, like if you've taken data structures and you know what a stack is, this is going to look really similar. This is going to look really familiar to what you did with like a standard stack in C++. Basically, pushing is going to put something at the top of the stack. Popping is going to take something off the top of the stack. So the stack is where a lot of, like when you're compiling your code, the stack is where a lot of really interesting information gets stored. So, for example, when you have like a return address or something like that, when you have some piece of metadata about a function, that's going to get put on the stack. It's also where a lot of like function arguments and things of that nature get put. So when you call a function, usually, at least on 32-bit systems, all of those arguments just go right onto the stack, and then the first thing that function does is it pops them back into registers so that they can be accessed more quickly, much more easily as well. So here's kind of a quick visual representation of what a stack does. You have a stack here, and you push something on, that's going to go onto the top of it. If you push something else on, that's going to go over the last value that you pushed, etc. Likewise, if you try to pop something off that stack, it's going to take the top of that stack and it's just going to yeet that off. It's going to take that last, or that top element off. So with that in mind, there's another kind of practice problem, if you will, here, another kind of piece of code that we're going to walk through together that utilizes these push and pop instructions. So we can see here the first thing that gets executed is we put 10 into EAX, and then we push EAX. So if we go back a second, you can see if we had something on the stack, now we've pushed 10 onto the top of the stack. So the top of that stack is going to be the value 10. We then move another value into EAX. So EAX gets overwritten, but we immediately pop EAX. So EAX here is the destination register again. So we're going to take the top of the stack, we're going to pop that off, and we're going to put that into the destination register of EAX. So if you remember, we pushed 10, and we pop, we're going to be taking 10 off the top of the stack and putting that into EAX. And then lastly, we just move that into EBX. So EBX at the end of all of this code will be 10. However, the stack is a really important thing, and I don't want to just breeze through it like that. I want to devote some actual time to talking about it and understanding how it works. Because as we do more work with reverse engineering, and especially as we start to get into binary exploitation, it's going to be really important to understand how this works and kind of what lives on the stack and what doesn't live on the stack. So basically, at the assembly level, at a very low level here, the stack is defined by two values. So you've got the base pointer, which on a 32-bit system is going to be EBP. That BP stands for base pointer. And then it's also going to have ESP, which is going to be the stack pointer. SP is stack pointer. And so you can kind of think of those as like the the difference between those two registers lays out the current area of the stack that you have to work with. So one interesting tidbit here is that the stack pointer is it's below the base pointer. So if you've ever used GDB and set a breakpoint for some reason, you may see that the base pointer and the stack pointer are kind of not really what you would expect, because the base pointer here is the bottom of the stack pointer is the top of the stack, and so you would kind of expect the top of that stack to be above the bottom of that stack. So that's kind of a weird little thing that you might not see coming, and the reason for that is because the stack is it grows upside down. It grows from these high memory addresses, and then it grows up towards low memory addresses. And that's something that has triggered a lot of debates in the security community, especially the reverse engineering and binary exploitation, exploit development crowd, of how to draw the stack. Because logically, it makes a lot of sense to think about it, where the piece that you push onto it, the top of the stack, would be at the top of the piece of paper. But the way that it actually gets executed on a CPU is kind of the opposite of that. And so some people draw it the right way, or I guess I should say some people draw it with the top of the stack being at the top of the piece of paper, which is the way that I draw it. So I'm completely unbiased here when I say that's the right way. Some people like to draw it the way that it actually is laid out in memory. However, I find that is a much more complicated way to be thinking about it. So just a kind of visual explanation here, or visual demonstration, because I understand that me talking for the last 5 minutes on how a stack works probably isn't actually doing it for a lot of people. It probably doesn't actually make sense for a lot of people. Here's a little picture of it. So you have high memory addresses. You see there's a bunch of these Fs. In hexadecimal, these Fs are going to be the maximum value for a byte. So this is going to be towards the maximum value of what you can store in memory. And then you're going to have all these zeros, which is the minimum value that you can store. So this is lower memory addresses. The stack is kind of towards the bottom here. It's kind of towards the high memory addresses. And the actual program code is lower in program memory. It has a lower address. But because the stack is growing, we've kind of drawn it with the low addresses on top and the high addresses on the bottom. So you can kind of see how that would get a little bit confusing. So to kind of visually represent the pushing and popping that we were talking about before, when you push something onto the stack, that goes at the top. So that goes at a slightly lower address. But then when you when you push something, it kind of goes on top of the last thing that you pushed here. So you can see the stack is growing. It grows up. However, it grows up towards lower memory addresses, which is a little bit backwards. So if you have, if you start out with these values for your base pointer and your stack pointers, you have OX40 and OX20. You can see they're OX20, which is 32 bytes apart. We push something, so that's going to change the value of ESP, because if you remember, ESP is kind of what points to the top of that stack, and EBP points to the base, so it points to the bottom of that stack chain. So when you push something, that's going to grow a little bit. So it's going to go down, that address is going to go down by 4 bytes. So now, instead of being OX20 bytes apart, so 32 bytes apart, we're OX24 bytes apart, so 36 bytes apart. And then if we pop once, we're going to get back to this state where the stack pointer pointed to OX20. So it was 32 bytes from the base pointer. Then if we pop again, that stack pointer is going to go up again by 4 bytes. So we're going to have a difference of OX1B, or 28 bytes. So that's kind of how the stack dynamically can grow or shrink, or your stack trim can grow or shrink based on the operations that you're doing. So that's all. That's probably the most complicated thing that we're going to be talking today is the stack. It's probably the most conceptually difficult thing. So just in case there was any confusion there, I want to reiterate once again, when you push something, that goes onto the top of the stack. When you pop something, it comes off of the stack, off the top of the stack. And then the stack is growing from these big addresses towards these small addresses. However you want to write that, however you want to draw that is totally fine, just so long as we're using the same terminology. The top of the stack is what gets pushed to and popped from. That's all that matters. And this is a really confusing thing. I know I still get tripped up by this, and a lot of people, especially people that are just getting started, do as well. So just wanted to reiterate and make sure everyone was on the same page once again. So we've talked about stacks. We've talked about all of these different types of instructions. And these are great, but when you write your code, it's kind of logically broken up into a bunch of different functions. You might call printf if you want to print something to the screen. A compiler isn't just going to cram all that code together, because that would be really inefficient. If you call printf twice, how does it then just like copy all of that code in printf twice into your program? Like, I hope not. Like, it should have some way to maintain that function structure so you can reuse code. And so when we want to call a function, those kind of get maintained at the assembly level, and we can call those with the call instruction. So we've talked a little about what a function is. It's basically just this reusable chunk of code. So if you want to print multiple things, you can make multiple calls to printf without all of that code just getting crammed into your main. And then functions can also obviously call other functions. So if you write a main function, that main function can call printf. Under the hood, printf may be calling some other functions to help that work. And then most importantly, when you finish executing a function, it's going to look back, it's going to figure out who called it, and it's going to return right there. And so that's a really important thing that I want to highlight, and I want to make sure that everyone kind of keeps that in the back of their head. Because next week, when we start talking about binary exploitation, that's going to be a really important thing to remember. So here's just a very simple function in C. It just has a buffer here, it has an array. It gets some data, so it puts that into the array, and then it calls put, so it writes that data. So you can get some input from the user, and then you can print it out to the screen. The way that these actual functions are going to be structured, though, you have that main function, so you have int main, and then main is going to be calling gets. When gets is going to return, it's going to remember exactly where it came from, so it's going to jump back to this line of code. And then it's going to call puts, and puts is going to remember where it came from, and it's going to jump back there. It's going to return right back where it came from. However, obviously we can have other functions calling, we can have nested functions. We can have functions calling other functions. So we can have main can call a function, and then that function can call another function within it. So in that case, the function, the graph of how these functions are going to call each other is going to look a little bit more like this. So main is going to call foo, and then foo isn't going to immediately return. Foo is going to call another function bar. That bar function is going to call baz, etc., and then they're going to chain those returns. So even in baz, you need to have some way that you can navigate back. You can remember where you came from. You can navigate all the way back to main and get to exactly the right address. And the way that we do that is by putting a little bit of information, a little bit of metadata onto the stack. So when we call foo from main, we put the address of the line that we came from onto the stack, and then we jump into foo and we start executing the code in foo. So basically, we're going to take that EIP register. EIP is a really special register that stands for the instruction pointer. That's basically just going to point to the piece of code that you're executing right now. You're going to push that, so that's going to be the top of the stack. And then you're going to jump into the code, you're going to execute it, and when you decide you're ready to return, you're going to pop that value off the top of the stack. And so you're going to pop that into EIP. So if we go back to that same sequence of calls here, we're going to push EIP in main, we're going to push the instruction pointer, and then we're going to jump into foo, we're going to start executing that code. We're going to get to a point where we need to go to bar, we need to call bar, and so when we use that call instruction, it's going to push EIP again, it's going to push the instruction pointer, it's going to jump into bar, it's going to start executing that code, and then when it needs to execute BAS, it will push that instruction pointer once again, and start executing. And then when we finish with BAS, we pop EIP, so we put the original value back into EIP, we jump back into bar, bar is going to finish executing, it's going to pop the value from foo into the instruction pointer, jump back to foo, and then foo is going to finish, it's going to pop that value back into the instruction pointer, which will push it back into main, it'll jump back into main. So basically this works because functions don't mess with other functions, like functions don't abuse the stack, they don't, like if you put data onto the stack, you clean that data up. And so you know at the end of your function when you're ready to return, you know the top value is going to be that, that instruction pointer. However, the way that we separate those through is kind of with the stack pointer, that ESP, and the base pointer, that EBP. So when a function is called, you kind of have to keep track of the base pointer as well. You kind of have to keep track of what part of the stack you have access to make sure that you're not writing data somewhere else on the stack where you might have a return address, or you might have some other functions like arguments. So you need to, in addition to pushing that EIP, you need to be pushing that EBP. And that's the way that we kind of remember what the old base pointer was, so that when we jump back, we know what the current stack looks like. And so that's how we have like function arguments, or we have local variables, or things like that inside a function, even after we get back from calling another function. So just to reiterate, when you call a function, you're going to push that that base pointer, and you're going to push that that instruction pointer. So over here, we have another kind of visualization. So I'm not just talking at you, you have something to actually look at, and hopefully that makes things a little bit clearer. You're going to have main. Main is going to have a stack, and it's going to have an EBP from whatever called main. It's going to have a return address from whatever called main. Main is going to call foo. It's going to have that return address in main. It's going to have that EBP from main, and that's going to have the kind of the section of the stack that's going to have all of your local variables, all your function arguments, all the things that should exist only within the scope of main. And then when main calls foo, the same thing is going to happen, where it's going to push that new base pointer that has all of the local variables of foo, as well as the instruction pointer, so that return address that's in foo, etc. So every time you call a function, it's going to push that return address, and then push that base pointer. So basically, as I was alluding to before, this all works because we trust other functions to not do anything mean to the stack. We trust them to only write to their part of the stack. And so that's kind of a bit of a teaser, that's a bit of a hint as to what we're going to be talking about next week when we get into binary exploitation. But yeah, basically before we talked about how the stack can hold a lot of different types of data, and I think the exact terms that we used were important control information, And so that's alluding to return addresses, basically. It has information on the flow of data, the control flow of data there. So it's going to tell you exactly where to jump to when you return. And then it's also going to have data of fixed size. And so that's going to be things like function arguments or local variables like we've been talking about. It might not necessarily, like if you have some giant, or if you have some data that you don't know how big it is, usually that's considered best practice to put elsewhere. That's not going to be safe to put on the stack necessarily. And that's also kind of a hint as to what we'll be talking about next week. But that kind of wraps up what I wanted to talk to you guys about today. On Friday, we'll be talking about, we'll be giving some more concrete examples. We'll be kind of giving you a hands-on demo of how this execution works in the real world. And hopefully that should clarify some things, but I wanted to make sure everyone was on the same page before we get to that. So if you've taken Comporg, if you haven't taken Comporg, in theory, you should all know everything that you need to know for Friday. And so with that being said, I think that's it for today, and I will see you on Friday.